Progress in modelling through distributed collaboration. Concepts, tools and examples. Hi there. In this talk I'm going to make a fairly strong claim that formal modelling in psychology is failing to live up to its potential due to a lack of effective collaboration. I'm then going to introduce some free and open source tools to facilitate distributed collaboration in this field. In the final section, I'll attempt to give a live demo of these tools. So first, and with apologies to those of you for whom this is too simple, what is a formal model? Well, one definition which I've used in the past is that a formal psychological model is one that unambiguously specifies transformations from independent variables to dependent variables. So, for example, in category learning, category structure might be one independent variable and classification accuracy one dependent variable. So as you can see in this figure on the left, we have 6 different ways of dividing 8 objects into 2 categories, the left-hand column being one category, the right-hand column being the other category. So the independent variable here is category structure. And then on the right, we have some learning curves. So probability of error on the y-axis, blocks of learning on the x-axis, and then the 6 types of problems as 6 lines. So here, probability of error is the dependent variable. So, as I said, a formal model unambiguously specifies transformations between independent and dependent variables. This slide shows an example of some of the formal models in psychology for those of you that are familiar with this area. Formal models are normally expressed mathematically or in the form of a computer program. As I've argued previously, formal models are important in psychology because they allow unambiguous comparison of the relative adequacy of theories. But, as I've also argued, relatively little progress has been made so far because the comparisons between models have just been too narrow. So, for example, in 2000, Smith and Minder compared the performance of 2 models on variance of just 1 experiment. The route to faster progress in formal modelling, I have previously argued, is to compare models across a much broader set of phenomena. Now, over the last few years, we've been trying to put that idea into action in our lab, but we've concluded that the goal is probably not achievable by any individual or small group within a reasonable amount of time, for example, 1 career. Now, we think collaboration would solve this problem, but a suitable framework for efficient distributed collaboration has been lacking until now. So next, I'd like to introduce a couple of concepts that I think are pretty important to the development of distributed collaboration. The first of these is the grid. Now, the grid, which is shown on this slide, is a way of representing the goal of broad comparisons of model adequacy and progress towards that goal. It's also an archival record of the success or failure of simulations of empirical phenomena. Each column of the grid represents a distinct formal model. The number of these columns, at least within the published literature, is knowable but probably quite large. The central problem, as we will cover in more detail later, is that software to implement these models is either not publicly available or available but incompatible with implementations of other models. Each row of the grid represents an empirical phenomenon within the explanatory scope of at least one of the models. Determining what these rows should be is a more difficult task than it might first appear, as I'm going to cover in a moment. Now, the matrix of cells that is defined by the rows, so the phenomena, and the columns, the models of the grid, poses a challenge in terms of sheer scale. Even with 10 models and 10 empirical phenomena, the grid makes it obvious that there's a need to run up to 10 models times 10 phenomena, or so 100 different simulations. Each journal article reporting work on a formal model has perhaps on average 2 to 4 such simulations. So even if the 25 or more journal articles that would at this rate be needed to fill a 10 by 10 grid actually existed, and they most likely do not as yet, discovering what has already been done is laborious, as no search engine indexes journals in this way. For example, if you wanted to search for simulations of Medin and Schaffer 1978 with the alcove model, one might use Web of Science to retrieve all papers that cite both articles. As of the middle of last year, that's over 300 articles. So, at a minimum, one would have to read over 300 abstracts to determine what simulations have been performed. And all this for one cell of the grid. Right, moving on to the next key concept. I'm going to propose that each row of the grid should be a canonical, independently replicated phenomenon, CIRP, or SIRP. We're proposing that each row of the grid should be an independently replicated phenomenon because modelling non-real results obviously wastes time. The waste of effort increases as the number of models increases. So 10 models equals up to 10 wasted simulations for each non-real result. Non-real results also potentially lead to an inaccurate assessment of the relative adequacy of models. A model should not be penalised for failing to accommodate a non-real result, yet inclusion of non-real results means this may happen. So, to guard against wasted effort and potentially misleading conclusions that come from simulating non-real results, we propose a minimum standard that relative adequacy assessments of formal models are restricted to independently replicated phenomena. Independent replication is beginning to become an accepted data quality standard in psychology. However, a criterion of independent replication, by which we mean no shared authors, is not always applied when choosing phenomena against which to evaluate formal models. For example, when the Generalized Context Model, or GCM, was introduced, it was evaluated against a single experiment which at the time had not been replicated. Now, there are a couple of objections that might be raised against independent replication as a minimum data quality standard for model evaluation. The first might be that attempts to replicate are rare in psychology, and that where replications are attempted, they're often unsuccessful. So, one fear is that applying a criterion of independent replication would leave no phenomena to examine within a particular domain. The rational response to such a fear is to determine whether one's fear is justified, and if it is, suspend modelling of that domain until such time as demonstrably real phenomena become available. Fortunately, some domains of psychology contain independently replicated phenomena, as illustrated later on in this talk. A second objection to using independent replication as a minimum data quality standard is that it's hard to define what counts as a replication. We think the concept of a SIRP is a pragmatic response to the perhaps inevitable uncertainty about what counts as a replication. The search for SIRP should, we argue, favour independent replications that are as close to being direct as the published literature will allow. We think the determination of SIRP is an area in which the concept of ordinal success is useful. No two studies in psychology have ever literally produced the same results at a quantitative level. In the SIRP approach, a replication is considered to be successful if the key results are statistically significant and in the same direction as the original study. Now, another aspect of defining a SIRP is to accept that some changes to stimuli or procedure may lawfully affect otherwise robust results. For example, Medin and Schaffer in 1978 published an experiment that is one of the most highly cited in the history of categorization research. That experiment has been independently replicated a number of times, and although there is debate about the generality of the ordinal result across different stimulus sets and procedures, there is now consensus that the ordinal result is robust within the experimental conditions employed by Medin and Schaffer. This experiment of Medin and Schaffer 78 is thus an independently replicated phenomenon in category learning. It may have boundary conditions, it's likely most psychological phenomena do, But when you run the experiment the way the original authors did, you can expect to get the results that they did. This seems to us to be a solid basis for the relative adequacy assessment of formal models. We think one strength of the SIRP approach is that it separates empirical phenomena from the interpretation placed upon those phenomena. A replication that is successful but whose authors favour a different explanation to the original study is still a successful replication. The theoretical legwork comes in the form of comparing formal models to phenomena. Separating phenomena from formal models should make it easier for groups with different theoretical approaches to work in a distributed, collaborative manner. Now, on to the third main concept in this talk. I'm going to argue that one of the main sources of inefficiency in formal modelling is the lack of publicly available model implementations. For example, at the moment, the majority of the formal models of category learning have no publicly available implementation. Examples include COVIS, Atrium, and the CRESS model. The amount of effort this wastes is large. For example, most of the work involved in a paper we published last year, which established that COVIS could accommodate a classic result in psychology, came from having to implement the COVIS model from scratch. The lack of a publicly available implementation increases the entry cost to using a formal model and hence disincentivises the exploration of models by those outside the research group that created them. So, our proposal is that another key resource for distributed collaboration is a freely accessible store of model implementation. Right, having set the scene and the need for certain things, it's time to introduce catlearn. Catlearn is the framework we have written to support distributed collaboration on formal modelling in psychology. Catlearn is a free and open source extension or package of the R language. Like R itself, Catlearn is made available under the general public license, which ensures that software is and will remain free and open source. The project title, Catlearn, was once an acronym, but the goals of the framework have outgrown the acronym and the word Catlearn should now be treated as an arbitrary proper noun. Before showing you the package, I'd just like to say a few words about some design decisions that we made. First of all, why is Catlearn based around R? R is perhaps best known to psychologists as software for statistical analysis. It provides similar functions to other statistical analysis software, but it also has many other features. Of particular relevance to formal modelling, R supports nonlinear optimization, the process by which formal models are typically fitted to data. Also, due to R's increasing popularity as an analysis tool for psychologists, situating Catlearn within R brings the advantage of a familiar environment that contains many of the tools needed to inspect and analyse the output of model simulations. R is also relatively easy to learn. As we shall see, another strength of R is that it provides a simple system for documentation to be incorporated within Catlearn. I guess one possible objection to situating Catlearn within R is that R code doesn't run as fast as code written in some other languages. In many cases, this is not an issue from the user's perspective, as code written in R still runs instantaneously. However, model implementations may in some cases benefit from being written in a compiled language. This can be achieved within R in a number of ways. The Catlearn package provides the framework for a free, open, documented archive of SIRP and model implementations, and also simulations. One thing we haven't considered so far, but which is important, is the issue of cross-compatibility of models. In order to facilitate model comparisons, each model implementation should, as far as is possible, require similar inputs and provide similar outputs. Of course, this correspondence can't be complete, as formal models differ in their assumptions about input representations and have different parameters. While some differences are perhaps inevitable, it makes sense to eliminate unnecessary differences in implementation. In pursuit of that goal, model implementations within Catlearn employ a stateful list processor schema. This idea is most easily described with the aid of an example, which is what I'm going to come on and give you now. Okay, the demo. So the first thing I'm going to do is show you a model implementation within the Catlearn package. What I won't have time to do is explain the details of the model itself, so I'll have to treat it as a black box. But for those of you who know this model, it's an implementation of the alcove model by John Kruschke. Right, so within catlearn, alcove is implemented by the function slp alcove, and that takes two arguments, so two bits of information, st and tr. St is the initial state of the model, so that contains both the parameters of the model, that's the first bit of the list there on the slide. It also contains the connection weights, which in this model start at 0, the position of the hidden units in a geometric space, and basically the information that you need to start implementing the model. You also have the TR array, that's the training array. The first few columns are not really that important for the purposes of today's demonstration. Starting at x1, x2, that's a representation of the stimulus, and then T1, T2 is a categorization model, so they represent the correct category membership. So the first item belongs to category 2, and we can ignore M1, M2 for the purposes of today. So slp alcove takes this information and it produces an output. The output is shown here, contains two components. First of all, there's the model's actual output, which in this case, it's a categorization model, are the probability of responding with each of the possible category labels. So on the second trial, for example, it's 60-40 for category 1. The output also contains the final internal state of the model. That's why we call this a stateful list processor. It contains the final weights and other setup of the model. Okay, and here's a really short live demo of the catlearn package. I'm in our studio here running R, and the first thing we need to do is just load the catlearn package. You have to have already installed it. There's information on the website to help you with that. We can then use the documentation included in catlearn to get some information about a model implementation. I've just run through the slp alcove model, and here is the help file for it, and a summary of its parameters and how it's implemented in some detail. Catlearn also contains syrups, of course, and here is one such data set. We just load in the data. It's called SHIN92 after the original experiment. You can see that we have some data from an experiment. We can get information about what that data means by asking for help again. This is the documentation of the syrup. It tells us what the columns mean, details of how the syrup was derived, and so on. Now, as we saw earlier in the talk, the simulation requires some kind of training matrix, so it can, some sort of input matrix, so it can run the simulation. We have SHIN92 train to do that for this syrup, so we can just run that function and put it into an array. You can see here we now have an array that looks much like what I showed earlier in the talk, with the stimulus representations and the teaching signals, category membership. And as before, we can get help on how to run this function. See here. Okay, we can also get information about a particular simulation that's been archived within catlearn. This is a simulation of that SHIN92 syrup with the alcove model that we talked about the implementation of in slp alcove. So in this next command, we just run that simulation across its default of 100 simulated subjects. You can see that runs relatively quickly. It's written in the underlying simulation is written in C. And if we have a look at that data set, we can see that although it may not be immediately obvious, it has the same data in the same order as the syrup. So these are each some probabilities which are in the same order as the probabilities in the syrup. That means that it's really straightforward to compare the model simulation against the output. We could do all sorts of things like R² or sum of squared errors. For the purposes of this short demonstration, I'm just going to do a quick plot. Each point is one data point. The x-axis represents the value in the syrup, so the empirical data, and the y-axis represents the model simulation of that point. You can see it looks reasonably good. One useful aspect of the archived simulations is that they can take different model parameters. They have a standard set defined by the modeler, but we can change those. So we can rerun that simulation with different parameters. That will produce a different output. And we can see by, for example, looking at R², how good that different fit was. And that isn't so great. There's an R² of about 0.73, which is lower than we got in the original simulation, although I didn't show you that today. The final thing I'd like to show you in this really brief demonstration is the ordinal adequacy tests. Now, I haven't really talked about these today, but these are a way of defining and assessing automatically whether a simulation captures the important trends in a data set. So the modeler defines what the key ordinal trends in the syrup are, and then the function tests whether the model has met those. So we run shin92 oat, and that tells us true. The simulation does succeed in fitting that data set. But if we run that again with the different parameters, then we can see that it doesn't work with different parameters. So the success of the model is parameter dependent. And that's the end of the short demo. So I'll just end with a brief summary. I've argued today that making efficient progress in the formal modelling of psychological processes requires a technological mechanism that supports distributed collaboration. Indeed, I believe the scope of the task before the formal modelling community is so large that the choice is between collaboration or failure. I've demonstrated a viable technological mechanism for distributed collaboration through the catlearn package, and I've illustrated its use through an example of the modelling of category learning, although the scope of the project is much broader than that. The catlearn package is free, open source, and publicly available. Now, I'm aware the approach I'm proposing here might be seen as controversial. Psychologists, one might argue, just don't work together in this way. Well, to the extent this is true, I hope that by taking on the initial work myself and with my colleagues, we can catalyse a change in our culture. The success of the kind of approach we advocate has clear precedents in other fields. Perhaps the most striking example would be the development of the Linux operating system, although I'll leave a discussion on that for questions if people are interested.